So what is the next title then? The next title is Depthwise Seperable Convolutions. We're going to explore an idea which will make the convolutional layers of a network much more efficient. And actually this idea was provided in the paper called MobileNets, as I've shown in the very early slides of this video lecture, maybe one of the previous lectures, is done by Google. So as you can see, the idea is depthwise separable convolutions. What is it? Guys, the key idea is actually separating the depth in the convolution. What does this mean? So guys, you're accustomed to using many networks now. You might have realized that after a few convolutions in the layers, the inputs to the next layer, which is the activation of the previous layer, they generally become multiple channels. Whatever, 16 channels, 64 channels. In AlexNet we have seen 256 channels as well. The depth becomes dense. So the heavy depths you acquire as you get deeper in the networks. Very good. So an activation with 64 channels has 64 different interpretations of that image. What does this mean? Actually, each depth represents a type of abstract feature. Just like one depth finding the edges of the image, the other depth finding the horizontal edges, the other one finding the blobs in the image, the other one finding the red parts of the image. So they are trying to get abstract features from the images. And there is something called separable convolution in signal processing theory, spatial separable convolution. Actually, it is related to the idea of factorization. For a 3x3 convolutional network, actually you can obtain, if the weights are separable, so-called separable, you can obtain a serially connected 1x3 and 3x1 convolutional neural network. So it is like you have an image, you convolve the 3x3 kernel, and you get an output image. If this filter is separable, actually these numbers are selected deliberately as separable. If we apply this kernel first, 3x1, then this kernel first, it is the same image. Because this filter is separable. You should just visit this website. It is a basic introduction to separable convolutions. If you're interested in what separable convolution is, it explains very well, whatever. So the idea is, in separable convolutions in spatial domain is this. However, what we are going to do is, we are going to do this separation in the depth dimension, not the spatial dimension, because in Inception module C, it is done in the spatial dimension. We are going to do it in the depth dimensions, guys. So, similar to spatial separable convolution, depthwise separable convolution splits a kernel into n separate kernels that do n separate convolutions, which n being the depth dimension here. Okay, I think you got the idea. We're going to separate the convolutions into one-dimensional parts, and they will be among the depth dimension. Very good. Let's see. So, guys, this figure is about normal convolution, standard. Standard convolution is you got a 5x5x3 filter, and the image is an RGB, so 12x12x3 RGB image. Just convolve this part, and you just move this part. If you have 64 of them, you will 256 of them, you will obtain 256 by the convolution, depending on the padding. So there's no padding at this example, so it's 8x8 by the depth being larger, because we have many of these filters, right? Wonderful. This is standard convolution. In depthwise separable convolution, each filter, so we've got many filters, we've got many of these filters, right? So each filter will be convolved with one of the dimensions here. Because in the previous case, each filter was, convolving with each channel, right? So one filter to one channel, one filter to other channel. So the red one doesn't touching the orange or yellow ones, and the orange one is not touching the red and yellow ones. So lesser multiplication. So let's try to understand this idea in another type of figure. This figure is from the original paper. You've seen the original paper. Original paper is this. If you go to this, no, this figure is not from the original paper. The figure is from this website, guys. So this is a very nice website as well. It's a review on separable convolution. It explains the idea very well, and they've got this very nice figure. I've just implemented on my slides. So guys, so that's the idea. You've got the activations here, and you will have the output here. Imagine there was, before I put this architecture here, there was standard convolution. Instead of standard convolution, what I do is I have the input to this layer, which is the activation from the previous layer, the feature being df by df by m. So df by df by m. M being the number of channels. So the visible m is 1, 2, 3, 4, 5 in this case. Okay? And the filter size is dk by dk by n. The original one, not in this figure. So I was going to apply it, this activation, to this filter, right? So if the example was standard convolution, in that case, the number of weights of this layer would have been dk by n, because this is the size of the filter, times the depth, right? And the number of multiplications for standard convolution I should have done would be dk by n by df by df, the huge number. We have seen the number of multiplications you have to do for standard convolution. You will remember this from the previous week's slides. Very good. This is what standard convolution is. Instead, we are going to apply this architecture. What is this architecture, guys? So this is the idea. So guys, in normal convolution, before we apply this idea, you have dk by m for each n channels. That's why we have dk by m times n. So this is a standard convolution example. If you visit the original paper, they've got it explained here in this figure very well. This is the figure, I guess. No, I guess it is here. Yes, this is a standard convolution filter, this figure. So this is the standard convolution idea. What is the idea for depthwise convolution? So the depthwise separable convolution is a depthwise convolution followed by a pointwise convolution. What does this mean? For each layer, I have a single filter, guys. So the number of filters is not n, but m. At the second part, we have this m number. So each channel, I've got a separate filter. If you have 5 channels, I have only 5 filters, guys. So each one of them has single convolution of each other. So depthwise single convolution. You will obtain m different outputs, right? So you have an m channel again. When you apply 1 times 1 convolution to this, so before we get there, so if you apply only one single filter to all these m channels, you will have this number of weights, dk by dk weights, m times. So the number of weights compared to this one is much lower. And the number of multiplications is, for each one of these, you will have this number of multiplications without the n, because in the original one we had this number of multiplications, but so dk by df times n. So this is the number of multiplications you do. But it's not finished. You have a channel. In the end, you do 1 times 1 convolution as well. Which is, why do we do this? Why do we do this? Let's continue this in the next slide.